Good morning, everyone, and welcome to the Oracle Machine Learning Office Hours. Thank you for joining today. One of the first questions was whether this was going to be recorded. So, yes, as all the Oracle Machine Learning Office Hours, this is recorded, and we share the slides afterwards as well. So today with me, it's Mark Hornick, Senior Director of Product Management for Data Science and Machine Learning. And we're going to be talking about the Oracle Machine Learning for R, an introduction. So Mark is going to be doing that presentation and also doing a demo. So the agenda today, we're going to just mention the next session. And then we're going to introduce Mark and let him talk about the Oracle Machine Learning for R. And we're going to end up with a Q&A. So we're going to let you guys ask questions at that point. So our next session is November 5th, next week, Machine Learning 102, clustering. So I'll be doing the continuation of our Clustering 101 session that I did in September. And then we're going to go into multiple dimensions, multiple attributes, and a little more into the comparing of the cluster techniques, and check the dimensionality reduction and importance that has on clustering. You can get more information about the oracle.com/machine learning or machine-learning. And you can go there and again find out all about our components, the different products that we have, different interfaces and APIs. And you can always get a free account from Oracle. So you can get a free account that includes the autonomous database. And even in the free tier, you actually have access to the Oracle Machine Learning in database algorithms and components and notebooks. So if you have not done yet, please feel free to go there and do that. So with that said, today's session is Oracle Machine Learning for R, an introduction. So Mark is going to talk about how to build machine learning models using parallelizing database algorithms, using the R formula-based specification, how to invoke user-defined R functions from SQL. We're using R engines that are dynamically spawned and controlled by the Oracle database, and taking advantage of running your own R functions in data parallel and task parallel manners. So Mark, thank you for joining, and the floor is yours.
Great. Thank you very much, Marcus. So hello, and welcome to this OML Office Hours session on Oracle Machine Learning for R. My name is Mark Hornick, Senior Director of Oracle Machine Learning Product Management. Now, in this session, we're going to learn about Oracle Machine Learning, and specifically OML4R, Oracle's interface to open source R integrated with Oracle Database. Specifically for our agenda during this set of slides, we'll begin with the enterprise machine learning pain points and give a brief overview of Oracle Machine Learning. Then we'll introduce OML4R, followed by a demo and interactive Q&A. And of course, if you have any questions during the session, feel free to post them to the Q&A in Zoom. So let's explore some of the pain points enterprise data scientists and other data professionals experience in their machine learning projects. For example, you might hear it takes too long to get the data or to load the data, or getting models into production takes too long or is complex. In other cases, there are concerns about data security, where the data is pulled into non-secure environments and maintained there. Yet others will cite scalability and performance as a major concern, among others. So this is where Oracle Machine Learning comes in. Oracle Machine Learning is comprised of a family of components supporting data science projects. Oracle Machine Learning focuses on interfaces for three popular languages: SQL, R, which we'll focus on today, and Python, which is coming soon. For interaction with Oracle Autonomous Database, we provide OML notebooks, which is based on Apache Zeppelin, with interpreters for SQL. We'll be adding Python soon to that and expanding to include R after that. The Oracle Data Miner user interface is a SQL Developer extension that enables users to create, schedule, and deploy analytical workflows through a drag-and-drop interface. Oracle Machine Learning for Spark, which also provides an R interface, provides machine learning in the big data environment with scalable parallelized algorithms. And coming soon are the Oracle Machine Learning AutoML UI, a code-free user interface that automates model building, selection, and deployment, and Oracle Machine Learning Services, a REST interface for model deployment and management, along with cognitive text analytics. So Oracle Machine Learning for SQL actually supports OML4R. So we're briefly going to highlight some of the benefits since many of these also apply to the R interface. The in-database parallelized distributed algorithms keep data under database control. So there's no need to extract the data to separate machine learning engines, which can be time-consuming and introduces issues for data security, storage, and recency. These algorithms are fast and scalable, and they enable batch and real-time scoring and provide explanatory prediction details, so you can even understand why an individual prediction is made. In-database machine learning models are first-class objects in Oracle database. So you can control access by granting and revoking permissions, audit user actions, and export and import machine learning models across databases. Now, when talking about separate analytical engines, such as open source R and even Python, we can cast this specifically as what we might call traditional analytics and data source interaction. Open source tools like R and Python, and even proprietary tools, normally require users to request data extracts from data sources, and then load flat file data and push results back to the data repository. For some users, they can extract data programmatically through various connectivity packages. For example, on Oracle Database with R, this may be R Oracle, or with Python, a CX Oracle. However, this is often problematic for larger data sets given internet bandwidth constraints. The challenges include data access latency, the need to change language, or even more critical, the need for data to reside in memory for the analysis. Most software and packages are single-threaded, meaning that even if you have multiple processors available, scalability and performance will be limited. When data is pulled from the database, there are issues of backup recovery and security. And for production deployment, there's the need to spawn analytical engines or load data and enable applications and dashboards to access the results. And this all adds up to unnecessary, or at least undesirable, complexity. So Oracle Machine Learning empowers data scientists and other data professionals with open source R by leveraging the database as a high-performance computing environment. Database tables and views are accessed through R data frame proxy objects with overloaded functionality that produces SQL transparently behind the scenes. The in-database parallelized machine learning algorithms are also exposed through a well-integrated R API. Data scientists and other R users can create user-defined functions and manage these in Oracle Database. R objects can also be stored and directly managed in Oracle Database, avoiding the need to deal with flat files. Since deploying open source solutions can be challenging, user-defined R functions can be invoked from SQL on premises and Database Cloud Service. Oracle also provides its own distribution of open source R for select platforms, and it supports R361. The functionality across OML's R interface is characterized by three functional areas. Using proxy objects, the transparency layer allows data scientists to operate on database data using familiar R syntax, overloading select functions that construct SQL for in-database processing. The in-database algorithms are exposed through familiar R interfaces, for example, using the R formula specification to indicate the target and predictors. And user-defined R functions can be invoked on database environments spawned and controlled R engines. Embedded R execution enables data parallel and task parallel processing. For example, an open source model can be scaled to large volumes of data for making predictions by requesting that multiple engines be spawned to process chunks of data in parallel. And OML provides all the supporting infrastructure to simplify your application implementations. So how do we achieve this? Well, OML4R introduces proxy objects that behave as R data frames, but they map to database tables and views. Here we show how the proxy data frame is a subclass of R's data frame class. Note that the structure of the R data frame, which contains the actual data, is really very different from the proxy object, which contains a reference, or a query essentially, to the data table or view. Now, this depicts the data query that corresponds to the iris table in the database. Just for your reference, here's a mapping between the R data types and Oracle database. The OML4R mapping follows that of R Oracle, the connectivity package, for this processing. For example, if the database has a column of type date or timestamp, this gets mapped to R's POSIX-CT data type. If an R data frame has a column of type POSIX-CT or date, this gets written to the database as type timestamp, and others can be interpreted similarly. Here's a set of algorithms supported in OML4R 151. Note that users can also take advantage of automatic data preparation, partitioned model ensembles, and integrated text mining, where you can identify a column as text, and the tokens will be extracted automatically and combined with the structured content. And through embedded R execution, users can augment functionality and algorithms using open source R packages, taking advantage of running user-defined R functions in a data parallel and task parallel manner if desired. Here's an example illustrating how OML4R embedded execution allows us to employ data parallel functionality to build multiple models in parallel, where data is partitioned by values from a particular column or set of columns. Perhaps we want to build one model per customer or one model per zip code to identify patterns or even to generate visualizations, perhaps using an algorithm from an open source package. With the data accessible as a database table or view, we ask our data scientists to write an R script that builds a model for an individual customer or zip code. This is then wrapped as a user-defined function that is stored in the R script repository in the database. We can then invoke this function, which spawns the number of requested R engines in parallel. We load the user-defined function and pass one partition of data to each R engine to build models until all the data is processed. These resulting models then, instead of being stored in flat files, can be stored in the database in what we refer to as the R data store. Now, how difficult is it to specify something like this? That's quite a process that's being introduced. Well, here's the corresponding R function invocation that allows us to realize this scenario. Using the function ORE groupApply, we pass in our customer data table and that we want to partition on customer ID. Then we pass in the user-defined R function that takes two arguments, the data that will be automatically passed in as an R data frame, and the name of the data store, where we want the resulting model to be stored. We build a model, which could also leverage one or more third-party packages, and use ore.save to store the model in the data store. To complete the groupApply function arguments, we pass in the string for the data store name, indicate we'll be connecting back to the database, and that we want this executed in parallel. We can also specify the number of parallel R engines we'd like explicitly. In all, this is just a few lines of code to automate this advanced parallel workflow. So with that, let's turn our attention to the demo. So here we're looking at the RStudio interface, and we have a script that is going to take us on a tour of OML4R. So the first thing that we're going to do is talk about the transparency layer. And to do this, we're going to load the library ORE. Now, for those of you who might be familiar with Oracle R Enterprise, the OML4R is the new name that we've given to Oracle R Enterprise, which we actually started back in 2010. So it's been with us for a good amount of time. We'll load that library. We'll then connect to the database. And so we're connecting to the schema in the database, the user, RQ user. And by specifying all equals true, we're going to get proxy objects for all of the tables and views that exist in that database schema. We can list what are the proxy objects that were created. Here we see we have two, narrow and ontime s. And we can use overloaded functions to get the class. Here we see it's an ORE frame, indicating that it's a proxy object. We can get the column names, what exists on the database table and now corresponding in our proxy object, and the dimensions, 1,500 rows and 9 columns. If we want to get some summary statistics on that, we can use the proxy object, and notice that we're using standard R syntax on data frames to get the first 5 columns, and the statistics that are being computed on these 1,500 rows is occurring directly in the database. Summary is an overloaded function. And what it does is to generate the corresponding SQL to compute those statistics in the database. So whether we have 1,500 rows or 15 million rows, there's no data movement involved. All of these statistics are computed in the database, and only the results are returned to the client. Now, we can bring data from the database to the client. Using ORE.pull, we're going to bring the proxy object data from the table narrow into an actual R data frame, and we see that that is its class. Now, if we look at the structure of that, just as we saw in the slides, we have the standard R data frame structure. If we look at the narrow structure, we see it's a very different beast. And in particular, if we look at the data query, we see that this is what is mapping to the table in the database itself. So let's do some column selection using standard R syntax. We showed where we have the column names and the dimensions on that. Here we have with ontime s about 220,000 rows and 27 columns. We can do a selection of some of the columns, again, using standard R syntax. On that, we see that it returns a proxy object for that. Can look at the first few rows with the overloaded head function. We can also project columns using column indexes, something that is very useful, obviously, in data preparation, and also to exclude columns using column indexes. Again, using standard R syntax, we can do row and column filtering as well. Aggregation, perhaps we want to say, how many flights are there per destination? Well, we'll use the overloaded aggregate function, passing in our dest column and saying that we want to get the length of that. And what we see is that the class of the result is also an ORE frame. That's because the results themselves could be relatively large. And we don't want to return those results to the client unless explicitly requested, perhaps when we invoke head. And so we see the results that were produced, but the bulk of the results are staying in the database. Another popular package is dplyr. And so we've overloaded that with ORE dplyr. That allows us to use the standard dplyr functions on the ORE proxy objects. So we can select columns, exclude columns as well, and filter rows, all using standard dplyr functionality. And for a little more involved example, here's the group mean arrival delay by airline. Now, another common data preparation operation is joining data. And so if we just had our data frames, we could create a couple here and invoke the merge function to join on the columns x1 and x2 across df1 and df2. But I also want to illustrate that we can interact with the database to drop tables and to create tables. So in this case, we're going to drop any tables that we might have created. Now, they're all not there, so that's fine. We're going to create 2 new tables from the data frames df1 and df2. Now, these exist as proxy objects in our environment, and we can merge those as well. So the merge is taking place as a join in the database, returning also a proxy object for us. We can also use ORE dplyr to accomplish the same thing. Now, there are some overloaded graphics functions. one of which is box plot. And here we see that if we wanted to look at a box plot of airline flight delay by day of week, we have the splitting of the data occurring in the database, and then we're going to invoke box plot on that and producing the results. So let's move our attention to machine learning. Here we're going to look at a classification problem using ORE.ODM naive Bayes. We'll use the dataset Titanic 3 from the package PASWR. Now, the first thing we'll do is we want to illustrate this operating on database data. So we're going to push the Titanic data to the database to create an ORE frame proxy object, but as a temporary table. This means that when we terminate our connection to the database, that this table will automatically be cleaned up. We don't have to explicitly delete it. So we do that, and we see that we have our class as an ORE frame, so it's a proxy object. Now we're going to use the overloaded if-else to do some recoding. We want to recode 0 and 1 as yes and no. And this will produce yet another ORE frame for us. Next, we want to do some sampling. So we're going to generate our random sample indexes and then get our train and test data sets using row indexing from OML4R. We see the class of the training data set is also an ORE frame. Now, what's really important about the sampling is that imagine that you have a very large table. And if you're using R natively to do the sampling, you'd have to pull that data in or have some other mechanism to get it in perhaps chunks, do the sampling and assemble your sample afterwards. What this is allowing us to do is simply identify what are the indexes that we want to have in our sample, and then we get exactly that data without having to pull that data from the database to the client. Next, we're going to create a priors object. So we have 40% yes, 60% no. And then we're going to build our naive Bayes model. So notice the R formula where we're going to predict survived using this set of predictors, passing in our ORE frame proxy object and the priors. That builds our model. And then we can do some prediction using the test data set. And we're going to return one of the supplementary columns survived so that we can pair it against the prediction in the generation of a confusion matrix, which we'll do shortly. But if we look at the results that came back, we see that we're getting the probability for no and yes. This is the supplemental column that we requested the actual survived value, and then the prediction. Next, we'll compute the confusion matrix in database using the overloaded table function. So all of the computations on this data occurred in the database by using SQL. So let's move to the next aspect of the functionality of OML4R, embedded R execution. The function we're going to work with to illustrate returning structured content, which could contain any structured result you wanted to return as a data frame, and also the images that you might generate using popular packages, even like ggplot2, or generating plots here, which we're going to do as random red dots. So we're going to create this function, and we'll execute that function locally just to show what it does. And it gives us our image here on the right, and we see the structured content being returned. Now, what we're going to do next is use the embedded R execution function, ORE.doEval, which essentially says, take this function, spawn an R engine, and run my function and return the results back. And by the way, I want to pass in some arguments, so I can do that naturally here in the argument list for doEval. We're going to do dev off. Let's reset the result. And then we invoke that, and we get our result. Well, here we see the PNG image that was generated and returned, and our structured content as well. Now, we did this by passing in the actual function, but we may want to store that function in the R script repository and invoke it by name. So here we'll drop the script if one existed. We don't have one in there currently. We'll create the script random red dots and pass in our random red dots function, and then we'll invoke that by name. So we can do that here as well. And we see we get another automatically generated result and the structured content as well. So we can do this in R, but we can also do this from SQL. And the motivation for doing it in SQL is that when you want to deploy your R results, many applications and dashboards already interact with SQL. And so if they could invoke their R functions without having to do any automatic spawning of the R engine itself, that makes life a lot easier for application developers. So when we come over to SQL Developer in this case, we'll use it to illustrate how we can invoke an R function from SQL. We're going to start with this. In the R example, we had random red dots that only generated a single image, but we'd like to illustrate generating 2 images and also passing some arguments into that. Now, we could have taken the same random red dots function and invoked it from SQL, and we can take this function, random red dots 2, that we're about to create and invoke it from R. So they're completely compatible from either interface. But in this case, let's take random red dots 2, and we'll execute this, and this stores it in the R script repository. Next, we want to invoke this function to produce the images. So we're going to use the SQL function, table function, rqeval. We're not passing in any arguments. We're going to accept the defaults in that case. We are indicating we want the PNG images to come back, and we're going to use the named function random red dots, which we just created up above. So when we run this, we see that we get 2 blobs, and we can view the images that were created. So on the back end, the R engine was spawned, the function loaded, the results produced, and returned in a table for us to access. So any application or dashboard that can invoke SQL can get access to these types of results. And these are, of course, trivial images, but any type of visualization that you would like can be returned as well. And we have our second image as well here. Now, to get the structured results, we can invoke the same rqeval, but with a different request. Here we're going to identify what is the structure of the result that's coming back to create essentially a table or a row set that we can interactively work with. So again, we're passing in the random red dots 2. We have no arguments, but we indicate what the result is. And you see here that our structured data frame that we returned is now being returned as a row set that we could create a table from. We could join with other tables and views, or do anything else that we might do with such a result. In some circumstances, you may want to have both the image and structured content returned together as an XML string, that then any application that works with XML can also produce these types of results. So here, if we execute this, you see we have the XML for the structured content first, and then later we will see the C data, that is the base 64 encoding of the images that were produced. We talked about passing in arguments. So to pass in arguments to our function, we're going to replace that initial null with a cursor that defines that we want the first argument, num.1, to have a value of 500, and num.2 to have a value of 800. And we do that using the standard SQL specification of selecting these from dual. When we run this, we see that we get our images back. And looking at these, we'll see that indeed we have significantly higher number of dots being produced in our image. So let's go back to our R environment. Just want to finish up with an example of a groupApply from R. So in this case, we want to build one linear model per destination to predict arrival delay. So we're going to get some destinations. We want to have our airports for this set of 7 that we're going to choose from. And we see that we have about 51,000 rows and 27 columns there. Now with the ORE groupApply, we're going to pass in our ORE frame, the data that we've just prepared that resides still in the database because it's an ORE frame, that we want to partition this data on the destination, so one of these 7 airports. And for each one of those, we want to build a linear model. So we want to predict arrival delay from distance and departure delay. So this will spawn our engines in the background, build one model per segment of the data. And we see that we have a list of 7 models, and let's look at 2 of them. We can look at the Boston one for starters, and so we see the linear model that was produced by this. And we have the one for SFO, another linear model that was produced. So at this point, we would just do some housekeeping. We could clean up, turn off our device, drop some tables, remove the script from our repository. And when we disconnect, remember any temporary tables that we created would automatically be cleaned up. We don't have to do anything further with that. All right. So I would like to go back to our slide presentation. So I'd like to talk briefly about the R Consortium. If you haven't heard of this, this is a vendor-led organization that promotes the R language and leads initiatives in support of the R community. It's committed to help evolve the R language by identifying, developing, and implementing infrastructure projects that support R. If you use R and are interested in becoming participating in, and shaping the R ecosystem, check out rconsortium.org for more details. The R Consortium has a broad range of members. Oracle is one of the founding members of the R Consortium and participates on the board of directors. You can contact membership at rconsortium.org if you're interested in joining or just have questions. So to summarize, why should you use Oracle for machine learning with R? Well, I'll highlight a few reasons. OML4R empowers data scientists and broader R users with powerful in-database machine learning with the benefits of R. By running within Oracle Database, users can perform scalable data exploration, data preparation, and machine learning, taking advantage of parallelism and even scoring optimizations at the Oracle Exadata storage tier, while using familiar R syntax and semantics. The integration of Oracle Database with the R open source environment makes it easy for users to deploy machine learning models and custom R scripts from SQL, simplifying data science projects and improving overall success. Since Oracle is where most enterprise data lives, bringing the algorithms to the data has major advantages. And of course, Oracle Database and Oracle Autonomous Database themselves also offer a long list of advantages for data management, security, performance, and scalability. So for more information on Oracle Machine Learning, you can go to oracle.com/machine-learning, or for more details and other resources on OML4R, go to oracle.com/go-to/R. And with that, thank you for taking the time to learn about Oracle Machine Learning for R. And at this point, we'll take any questions that you may have.
Perfect. Thank you very much, Mark. That was a great session.
Thank you.
So I've answered one question regarding the memory. So Abhilash Sahai was asking if there's a sizing guide to determine addition compute resources required if you start using OML4R, right, against the Oracle database. So I mentioned that blog that you created on the memory sizing for Exadata. That
Very
might
good.
be a guiding, light perhaps to understanding that that processing, right?
Indeed, I think it largely comes down to the types of operations that you ultimately are going to run and what degree of parallelism that you want your users to have. You really have to take into account the volume of data and how complex your solution needs to be to meet your time constraints. And usually the best thing to do is to try out some of the actual scenarios that your data scientists are likely to encounter. And if that will give you a sense of not only how big of a machine do you need, but given the size of machine that you have, what type of specifications should you be using so that you can really optimize your performance in that environment?
Mm-hmm. Yeah, that's excellent. So we have a few more questions coming in. What's the difference between the ORE ML versus the open source R package ML? So machine learning on Oracle versus the machine learning open source, I guess.
Sure. Well, I think there are two things to keep in mind. I mean, there are the open source packages, which have their implementations that occur in the R engine itself. So in order for those algorithms to work, barring some exceptions, the data is pulled into the R client memory, and then the algorithms process that. And normally, those are serial executions, meaning that there's no parallelism used there. So your scalability and performance will be indicative of that architecture. Now, with the in-database algorithms, those are implemented to operate inside the kernel of the database. So the implementation is sort of right next to where the data resides. There's no additional security mechanisms that have to be involved to access the data. You're not pulling the data into a separate environment. You're actually building the models right there in the database itself. And these algorithms are parallel. So they've gone through sort of a significant design to say, how can we take these types of popular algorithms that we might see in R or Python or other environments and make them parallel so that they perform very well, can take advantage of multiple processors, but also can be distributed, meaning that if you have multiple nodes, think of like an Exadata box that has multiple nodes that you could be operating on, that the data can be distributed across those and the processing can be distributed across those. And then the results combined in such a way that you get a single unified model. So that's really some of the key differences between the implementations there. Now, we have, as I showed, a wide range of algorithms that are exposed through the OML4R interface, and we'll be expanding those in the future. But through the embedded execution, one of the benefits there is that while we're not claiming to automatically make parallel open source packages, that's really an unsolved problem, so we're not claiming to do that. We are saying, though, that you can get some benefits by using embedded execution in a data parallel or task parallel manner. And so in a data parallel perspective, we're saying if you can separate chunks of the data, partition that data, say, according to, as I showed in the example, zip codes or customer ID or things of that sort, then you can build smaller models on those and have the underlying OML4R system help you with that, right? Take over a lot of the rote programming that would have to occur for you to do this manually. We've already done it. It's already tested. It's already part of the environment. You simply have to invoke it. So I think that's another way where you can get the scalability using open source packages in combination with the embedded R execution. Something that I mentioned in the slides, there was another notion about scoring. And if you build an open source model and you wish to score it on, 100 million records, you can do that in parallel also. There's a function called groupApply, and that allows you to chunk out some number of rows, 10,000, 100,000 at a time, and do that across multiple R engines so that you can process that scoring result much faster because you're introducing this embarrassingly parallel capability. And the results are all going to stay in the database and can be exposed as a single table. So this is another way that you can achieve a greater degree of performance and scalability with open source models.
Perfect. Thank you, Mark. And also that, I think, answers the second question Venkata had, which is then if we use third-party RML packages like NNet, right? Mm-hmm. Will the database parallel? And you already answered that. That is unfortunately no. We don't have a the magic bullet to parallelize the
That's
neural
right.
network open source packages. So there is a good one. Does embedded R execution works with autonomous data warehouse?
Yeah, and that's something that is on our roadmap for the coming year. It's not there currently. So right now you have access to OML4R, which, by the way, is included free with your Oracle database license for your on-premise Oracle database installation, as well as with database cloud service or database as a service in the Oracle cloud. So that's what you can use today for that. But we will be incorporating OML4R into Autonomous Database in the year ahead.
Excellent. We have, now that Oracle Machine Learning is included in every database edition, have you seen an increase in the use of OML in our existing customers?
Well, the challenge with finding usage information is we don't have access to that. So, I mean, if you look at the broad base of customers that are using the database itself, now that they have access to the machine learning, they're free to use it in whatever way that they'd like. We don't have a way of sort of looking at what customers are doing with that. So to say definitively yes or no, we don't have access to that level of information. However, we do see that customers are asking plenty of questions and are interested in how they can take this to the next level. So there's no definitive result that I can give on that question, unfortunately.
Okay, perfect. Then before I go to the notebook questions, there's another question for customers without an important volume of data in their databases, say like less than 500 gigabytes. Is it worthy for them to use OML4R instead of open source R? If so, why?
Sure, that's a great question. I think that the reason is whether you have extremely large data or even modest data sets. The question is, how easily do you want to be able to deploy your solutions, right? And for that, I think you could look at what we showed with some of the open source models that you may have produced and say, well, I'd like to be able to invoke those easily in my applications and dashboards from SQL. Or maybe I want to have an easier workflow between my data science team and my application development team. So imagine that your data scientists are writing their R scripts and they're storing them in the database. They're all tested and they know how they can be validated through a SQL invocation. And then they just pass off to the application side of the house, invoke the SQL script to get the structured results that you need to populate a dashboard or support an application, or images. If there are some visualizations that can be used in applications and dashboards, those can be immediately handed off. And so it makes it very easy to work with that. In addition, if we are looking at, even from a scalability standpoint, for open source models, okay, 500 gigabytes or less worth of data may be manageable in some environments, but in certain circumstances, depending on what the algorithm that's being used, you may want to take advantage of the data parallel and task parallel capabilities that OML4R offers. So I think there's, if for the large data sets, certainly the in-database model creation is it offers the scalability and performance that you need for that. But you also may get benefits from the other aspects of OML4R. Just one other thing I would say about the in-database algorithms is, even if you don't need the scalability, there are features that are associated with the in-database algorithms that you may also want to take advantage of. We mentioned about the partitioned models. This is an automated way of saying, I want to just identify a column or set of columns that I would like to partition my data on and have a single model be produced from that. Yet behind the scenes, it's really producing an ensemble of sorts that will simplify creating multiple models, one for each of the partitions, and allow you to score it as a single model. Or the integrated text mining, where you can identify a column of text in your table of other structured data. And so I'd like you to automatically do some tokenization of that and incorporate that with the rest of the data in building the model. There's also the prediction details. Not all algorithms are going to provide you the understanding of why was this prediction made? What were the predictors that most influenced the prediction? And so you can get that with the in-database models. So there are a number of reasons why you may still want to use OML4R, even if you don't have large volumes of data.
Okay. And then where can I find example R notebooks? And I think if you allow me to share, I wanted to show the GitHub.
Sure, go right ahead.
So I think it's very easy, right? If you guys go to github.com/oracle/oracle-db.examples. So these oracle-db.examples here, you can see all of the examples that are included with the Oracle database and work with the Oracle database. And in there, we have our folder, machine learning. So if you click on the machine learning, you have two places for R and Oracle R Enterprise and OML4R. Basically, in R here, right? So you can click on R, and then you will go for OML4R. And in that folder, you have lots and lots of different basic demos and vignettes and tests and examples, right, for all of the components we have. And then the other place under machine learning is in the notebooks. Right now, we only have, for R specifically, we have only one, the clustering here, that is on that side. But we are going to be increasing and uploading more OML4R examples as well, based on Zeppelin, right, in this case. So you can import that into Zeppelin and then take a look at that example right there. All right. And then another question, do we recommend customers to use OML packages in separate database environments than their production databases?
To some extent, that's a decision that needs to be made on an individual basis. I think that depending on whether or not you are able to partition your production environment, that maybe you want to have some resources dedicated to your data science team, that's one possibility. In others, you may want to have a development environment that has direct ties to the source data that you can then work on as a single version of the truth. Or maybe you're doing a synchronization between the two databases so that your data science team can develop what they'd like in that environment. And then you can also export models and import them. So you may export the models from a development environment and import them into the production environment for scoring purposes. Same thing with, obviously, the user-defined scripts that you'd be writing user-defined functions in R and move those from one environment to the other.
Okay, I think that's it.
All right. Well, thank you very much for your attention, everyone.
Thank you very much, guys, and see you next week. Thank you.